Hey everyone, happy holidays. In this video I'm going to be walking through my exploit for RandomPresent, which is one of the Pwn challenges from this year's Xmas CTF. By the way, the challenge, the CTF was very fun, and I want to say thanks to all the people who ran it. Learned quite a lot from it. So in any case, this is RandomPresent. It ended up being worth 50 points because of so many solves, but I'm just going to be walking through my solution. I'm pretty sure there were quite a few different ways you could solve this, but in any case, sometimes you just don't get what you desire, and we're given the challenge as well as a server address to connect to. So the first thing we do obviously is to open up this binary in Edit Pro, and we can just kind of take a look at what's going on here. So just glossing over, we don't have to take a look at every single thing, just look at the important parts of this. We see that there's two calls. The puts here basically displays, this is easier than you would think. Santa allowed you to rob me. And then finally we have a call to gets here. And this right here is basically where the vulnerability is call to gets. And the argument to gets is going to be located in RDI, as we know, in the 64-bit calling convention. And if you didn't know that, you can just awesome Wikipedia page here, and you can see that for let's see, yeah, the x86 64 calling convention, we have for the Linux. We have RDI, then RSI, RDX, RCX. And so you can see a little bit of that inside of this as well, if you look at some of the calls to set vbuff. But in any case, the first argument is an RDI, and that's basically the character buffer pointer that will be read into from standard in. So RDI is set to RAX, which was set to RBP plus var20. In this case, yeah, so var20 is just, that's simply -20. And if we convert that to decimal, we can see that that's 32. So this is located 32 bytes below the base pointer. So at this point, we can already kind of formulate an exploit. What we're going to do is basically overflow the buffer and take control of execution. At this point, there's kind of a branch. We can either go the route of writing shellcode and returning to it on the stack, or we can do a Ret2Libc type attack. The first method is not possible in this case, because if we go and open up this, and you can see the binary here, you can open up a Python script and load the elf to do a quick check on the security for the, make sure you import the Pwn libraries first. And if you look here, we have NX enabled, and NX basically means non-executable. The stack is non-executable, so you can't really put shellcode on the stack. So we really want to do a Ret2Libc attack here. But the problem is there is dynamic library being located here, and also there's stack layout randomization. So in other words, we cannot find an address that we can return to every single time and expect to get the get a shell running. So to address this problem, what we want to do is basically find a way to leak an address from libc in order to return to libc. So in order to leak an address from libc, what we need to do is go to our friend here, the global offset table, which contains a bunch of different functions and pointers that are loaded into this into the data segment of our binary from libc. So it starts here, and the first thing that is loaded is the libc start main pointer. Libc start main is basically a function in libc that sets up the environment for the and calls the main function of our program. And it's not really important that we know that, but it's useful to kind of see what we're doing here. So basically, if we can leak this pointer, leak this address, then we can find out the base of libc, given that we also know the libc version, of course. which for our local machine won't be a problem, but for the one on the server it could be a little bit more of a challenge. But in any case, our goal is to leak that. So how can we do that? Well, we just look at main and we see that they're called a put, so we have this puts function that we can use. So if we just call puts with the pointer set to that address in the global offset table, then we can read off that address. So it's very simple at this point. We just need to call puts with hex 600ff0. But it's actually not that simple, because if we go back, we realize, yes, it is a 64-bit binary, so we can't just simply add the address to the stack and call it. So instead, what we have to do is find a way to load a value into this RDI, into the destination index register. And that's actually not a very, at first that doesn't seem like a very simple thing to do, but if we think about it for a bit, we saw some things in return-oriented programming that allows us to interact with the registers from the stack. And of course, that happens through pushing and popping instructions. So what we really want is a way to pop something into that RDX register, or RDI register. So here, I've assembled RDI, pop RDI in return, which is the most straightforward gadget that we could get. And we get just 2 bytes, 5F and C3. So if we go into IDA and actually do a byte search, sequence of bytes 5F, C3, we get 1 hit in the libc CSU init. And if we actually jump to this into our code, we see that the instruction here is actually not a pop RDI, but instead a pop R15 and then a return. So what in the world is going on here? If we go to the options here to display some opcodes, and we set that to something greater than 2, we can see in fact that pop R15 is actually compiles to 41 5F then C3. So in fact, this instruction, the later part of this instruction, actually gives us what we want. And this is just a testimony to the density of the x86 instruction set. It's exactly what the original paper on the return-oriented program was talking about when it was saying that due to the density of the x86 instruction set, instructions can be found inside of instructions. But in any case, we can return to here 40077B and basically get a pop and then a return, which is exactly what we want. So let's go ahead and open up Notepad just to keep track of this. So we have a pop gadget, and we know that's equal to 40077B. So that's what we want to, that's the first address we want to return to after overflowing our buffer, which, by the way, we should look at that right now and see that it's RBP minus 32. So we need 32 times some junk. And then we need to overwrite the save base pointer, which is 8 bytes in 64-bit version. So 8 times more junk. And then the first address we need to go to is the pop RDI. So what do we want to pop into RDI? Well, we wanted to call puts with the address 600ff0, so that's probably what we want to put into RDI. So that needs to go next. Let's just call this libc start main pointer. Very straightforward. That is equal to 600ff0, and we will put that here. Then after this, we have the proper thing to call puts now, so we can just go ahead and call puts. So how do we do that? It's very simple. We just call puts here. We look at the address is 400550, so we can just that. Here is another gadget, and set that at the end of our thing here. So what we have here will enable us, should enable us, to leak the address of one of the functions in libc. So to test this out, let's go and create a Python script. Present Python. So first we're gonna import pwn, and we're going to start a process with the local RandomPresent binary. Then what we're going to do is make a ROP chain. So the base of the ROP chain is going to be our garbage, which was 32 times something plus 8 times something else. And notice that I'm putting B's in front because I'm actually using Python version 3, where the Pwn tools packing addresses are actually going to be bytes instead of just a regular string. So yeah, but it's mostly the same. So that's our base. Then we have a lot of stuff here, so let's just copy that, and now we can start constructing our payload. So our ROP chain is going to be equal to the base plus the RDI plus libc start main plus splits. Do that. So, oops. All right. So, cool. So what we're going to do first is basically buffer out the text that it sends, and then we're going to send the payload and then see what we get. So let's run Python, and we see we got some stuff back actually, and the stuff we got back looks like we got 7F, then something, then something, something. So this looks promising, but just to be sure, we should see exactly what kind of data we're getting back. So we're going to run with this local debug, which will allow us to see the exact bytes that we're getting. It's basically a hex dump of all of these communications. And in fact, we can see what we sent as well. So this was our garbage. This was the gadget to pop RDI return. This was the address that we wanted to read from that contained libc start main, and then this was the address of puts. And in fact, we got 7 bytes, and it looks like the address is 7F866AFE10D0. And this is actually different from what we saw before, which was something like this. So clearly we can see that the address layout is being randomized. And one of the comments here is that we know that it's going to be little endian here because the way that puts works is that we set it equal to the bottom, the lowest address of this libc start main. So it's going to start reading from the least significant byte of the address, and it's going to go up, and that's why we get something like this. And actually, for 64-bit binaries, the largest addresses are located at 7F. So this is actually a promising result. We can run it again, and we see we get something a little bit different. So this is probably where the random part of the RandomPresent challenge name comes from. And of course, we get this new line at the end here, which we're not too concerned about because that's just what puts does. But in any case, to finish off this challenge, what we need to do is parse that value that we get. So to do this, I'm going to do a little trick here. Basically, I'm going to import from the crypto library, crypto number, something called the bytes to longs. So what I'm going to do is take this and do a bytes to long p.receive line. Oops. Like that. And what this will do is basically convert bytes to long of p.receive line, and because it's little endian, I have to flip the order, right? And I also don't want the last 2 characters, which are 0 and A, because that's just representing the new line. We don't really care about that. So yeah, this will turn this into the address that we want. And just to see what this looks like, we can just log it. Address of libc start main. This is the absolute address. Oops. And from this, we can actually calculate the base of our libc. So at this point, it's a good idea to start a libc object or an elf object with our libc. And so I know that on my local machine, the default libc library is going to be that libc2.26 shared object file in that directory, so I can just do something like that. And so at this point I can just set the address, which is the base address, to be equal to this libc start main minus the libc.sim. This is basically the offset of this function inside libc. So this is a real function inside of libc. And so we can also log that. Great. And so let's go ahead and run this and see what kind of stuff we get. So, oh, my bad. libc address. Oops. Let's try it again. Great. So as you can see, we got that 7f, 3f, 1dcd0 here as the address of that function, the absolute address of that instruction, and the address of libc is just this value here. And we can be confident that this is accurate because we can see that the libc is loaded at the boundary of what looks to be 16 to the power of 3 boundary, because these last three hex values are 0. Yeah. So we can be confident that this exploit has worked, at least on the local machine, that the library was correct and all that. So to finish this exploit, all we need to do is send another payload that calls system-binsh, as you would do in a regular Ret2Libc attack. But in order to do that, we need to call the gets function from main again. So at this point, we could basically put another gadget here, but the problem with that is there's this leave and return, which basically screws up with our stack setup here, because what we have is pretty good. So instead, what we need to do is go here at the beginning of main and just run the whole thing, just to make sure that our stack is still the ROP stack, the messed up stack, is still intact. So we actually need to go here and use this address. So I'm gonna add one more here and go 400676, and then go here and put that as part of the first payload, and then return to it. So after we call puts, we're just going to return to main. So after that, now we get to do it all over again. We get to submit a second payload. So at this point, we can craft it still with the base, and now we need to call system-binsh. So it's kind of the same situation with the puts here, puts with the libc start main pointer address. This time with the system-binsh. And binsh is a string, which is an argument. A string. We need a pointer to that string. So we still need this pop RDI gadget as we did above. The location of the string can actually be found inside the libc with libc.search, and you can search for strings. So we do binsh. And this is actually a generator object, so we need to use next to actually get out a value. So this will give us the pointer to binsh, which will be popped into RDI. Oops, just set RDI there. It should be pop RDI. And then we need to do libc sim system. So this will be the address of system. And after we do this, we're pretty much set to go. So we will go ahead and receive line twice, just to buffer out, again, because we're going to get that stuff printed out, and we're going to send line that. So let's go ahead and run this and see what happens. So we get this, and okay, so what happened was we sent our first payload, which now has the same stuff as we did before, but now we have an extra gadget to the main function, and we received some bytes again because of course we returned to main. But more importantly, before that, what we got was these 7 bytes, or technically 6 bytes, that had the address of libc start main, which allowed us to calculate the address of libc. And then again we sent 41 bytes, this time with system -h, and now we have the interactive mode. It looks like we have shell, so let's check. Indeed, we got shell. So we can see, I can see all my stuff here. So it works on the local machine. Now finally we just have to do it on the actual server. So instead of a process, now we need a remote. And so we go back to here and we netcat this to here on this address. So let's see, 5. And the library that was used for this was actually the libc.so.6. So we'll use that one. And in fact, there's still something weird about the library. I don't think it's actually even that library, but in any case, let's go ahead and write it and see what happens. Let's see. Ooh, no such. Second. libc.so.6. I think that was the library. Oh, yeah, of course. This is. Alright. So, again, the same idea. This time just with a different library, but we see the address of libc actually looks normal, so we can be pretty confident that what we got was actually correct. And from what it looks like, we have shell. Let's just cat the flag, and we get the flag. Xmas. Random Christmas presents are so fun. So I hope you enjoyed this video. It was kind of long, but this was a really good demonstration of the return-oriented programming in combination with the ROP-Ret2Libc attack that we're also familiar with. And again, the binary here is not particularly complicated, but we had to find a gadget that happened to be in this weird function here, and it wasn't even the right instruction, but it all turned out fine in the end. So yeah, happy holidays. I hope you enjoyed it, and I will see you in the next video.